Hey, topic 6.9, Hess's law. All right, let's do this. Hess's law is yet another way for us to determine, sorry, someone just rang my doorbell. I'm not gonna get that. Another way for someone to calculate the heat of a reaction. It uses, I'm going to call this Hess's law of summation. And I feel like in a sense we've been using this law already, but not of summation. All right. But Hess's law is a state function. He's like, enthalpy is a state function. And what it means to be a state function, right, is that it is independent of the route taken to get from reactants to products. And let me explain to you what I mean. What matters is where we start and where we end. It doesn't matter how we get there. Okay, it doesn't matter what reaction mechanisms occur, what elementary steps happen. It doesn't matter what's on top of the activated complex. It doesn't matter if we stop at the store and pick up our friend on the way to school. What matters is we started at home and we ended up at school. That's what that means. All right. So that allows us to take other equations and manipulate them and add them together, cancel reactants and products that are the same on both sides, and add up reactants and reactants that are the same, or products and products, and end up with another equation. And we can use this to calculate the heat of the reaction, right? We've used bond energies where we broke bonds and formed bonds. We use standard enthalpies of formations where we formed and unformed compounds. Now we're going to take some set of given equations and use them to calculate the heat of a reaction. So here's a practice problem. This is from the PowerPoint, whatever slide I said it was in the little notes part. And we have our target equation here, right? We would call this in our notes our target equation, because that is the equation we are trying to get, right? And what I always do is and what we are also given are these other equations here. And we are to use these equations and their enthalpies. Oh, that's what I was going to write up there. These equations and their enthalpies in order to calculate the enthalpy for this equation. Okay. And what I needed to say up here is just two things. If a reaction, I'll write the whole word out, is reversed, right, then the sign for delta H changes. Okay, right, because we know delta H for the forward is equal to negative delta H for the reverse, okay? And if the coefficients are multiplied or divided, multiplied by 2, then delta H is also multiplied by 2, etc., right? Whatever you do to the coefficients, you also do to your delta H value. All right. So now we have our target equation. We have the highlighted equations in color that we are to use. I'm going to always take the same approach. I'm going to look at the first reactant, and it's 2 carbons. And I see that in my second equation, I actually have carbons. However, even though they are reacting as I need them to be, so I don't need to reverse it, I only have 1, but I need 2. So I will multiply this equation by 2. And I'm going to rewrite that. And notice they just wrote solid instead of graphite. That's fine. If they did it, you can do it too. Not a big deal. Make sure you actually multiply everything by 2, right? So that times 2, that times 2. States of matter are important here. And since I multiplied that by 2, I will need to multiply my delta H by 2. So it is now negative 787 kilojoules. Okay, and that's per mole of the reaction as written. It's no longer per mole of carbon. Okay, the next thing I'm going to do is I'm going to go to my next equation, or my target equation. I'm going to see my hydrogen. I need 1 hydrogen as a reactant. So I see that right here. I've got 1 hydrogen as a reactant. It's exactly where I need it to be. So I'm just going to keep this as is and write H2 gas plus 1/2 O2 gas yields H2O liquid. And the delta H for that is equal to, and I apologize, this should be 0.0. I preach sig figs. I should do sig figs 0.0. I just looked up. I think I'm ADD in my brain. All right, and then this delta H, I apologize, is negative 285.8. I've got that from right over the blue, and that's kilojoules per mole, and that's per mole of the reaction as written. And then lastly, notice that, go back to my target equation. I've got C2H2. I got 1 molecule produced. Right here in my first yellow equation, I have 1 molecule reacting. So I'm going to need to reverse this equation. So in the reverse, I write my products first. So that's 2 CO2 gas plus H2O liquid yields, and then I will write my reactants. The C2H2 gas plus the 5-2O2 gas. And because I wrote my reaction in the reverse form, I need to look at my delta H, which is negative 1299, and I need to make that a positive 1299. All right, and that is 0.6, and that is kilojoules per mole of ethine formed, or reaction in this case. So I've used all my reactants, these 3 over here, so that tells me I should be done. I have also made it through here. So what I'm going to do is I'm going to ensure that my overall equation at this point is actually the same as my target equation to ensure that I have not made a mistake. And I'm going to do that by canceling and adding. Adding like canceling opposite terms, if that makes sense. I don't know if that's what you do in science. But notice right here, I've got 2 carbon dioxides reacting, 2 carbon dioxides produced. So those will be canceled, right? I also see that I've got liquid water, 1 molecule, and here's 1 molecule, or 1 mole and 1 mole. So those will be canceled. Notice here, guys, that I have 5/2, which is 2.5. And right here, if I add these up, that's 2.5. So those actually all cancel as well. And what I'm left with is 2 carbon solid plus an H2 gas yields the C2H2. It's called ethine. It would have a triple bond. That's why it's an ine. It's balanced as it should be. And remember, the goal was to get the enthalpy of the reaction. All right. And we add that together. I've got on negative 787 plus negative 285.8 plus 1299 0.6 equals, and I've got 226.8 now, and that's kilojoules per mole of ethine. It's also, notice, it is the formation equation. So this could also be our standard, as we don't know if it's standard, if the conditions here were standard or not, right? But I would like to point out that this is positive. And notice that all we did was, well, we did have to break this bond, but we formed these bonds. That tells you that this is really unstable, right? It didn't release energy in forming, it gained energy. Not a very stable compound, all right? Okay, let's look at one more, guys and girls. Let's look at one more. I think this will do it. This one's going to be a little bit different, but the same. We're going to add some things that we've already done. Okay. Calculate the standard enthalpy of combustion of propane-2-ol. Okay. Well, given the following data. So this time we don't have a target equation, nor do we have data. So we need to create all of those for ourselves. Let's just do that slowly, one step at a time. Standard enthalpy of formation. Standard enthalpy of combustion, rather, of propane-2-ol. I'm going to simplify this. I've got 1 carbon, 2 carbon, 3 carbons. I've got 3, 4, 5, 8 hydrogens, and I've got an oxygen. I'm going to simplify that for myself, okay? And I'm going to create the target equation, because it tells me that the target equation is the standard enthalpy of combustion. So I will take the propane-2-ol, and I will combust the propane-2-ol, and we will get the carbon dioxide, 3 plus the 4 H2O. That makes 3 plus 4 is 7. Did I do that right? I'm going to make this look more like those. Sorry. Okay, I've got 3 plus 4 is 7. 7 minus, I want to make sure I did that right. I felt like I had a 9 last time. 7 minus 1 is 6. So I just need to put a 3 right here before the oxygen, right? I hope I'm right. I really felt like I did something. I had a different number there last time. Okay. And we are looking for the delta H for this reaction. Let's look at what we're given, guys. We are given, let's start with something green, the combustion for graphite. So let's write that equation right here, the combustion for graphite, and we'll keep everything organized. This is our standard enthalpy of propanol, our target equation. Let's write the combustion for graphite. That's C graphite combusts, and that, as you would predict, is going to make CO2. You will not have to know that. The enthalpy of that process is negative 393 kilojoules per mole of graphite combusted. We've also got another equation provided to us here, and that is the combustion of hydrogen. So let's take H2 and combust it, and let's get liquid water. Right, that would be a gas, and that would be a gas, and the delta H for that process is negative 286 kilojoules per mole. That's our green here. And let's get our formation. Let's get our formation of propane-2-ol equation. All right, so we'll write, oh my goodness gracious, we'll write that here, the formation of propane-2-ol equation. All right, That's going to be, we're going to form the C3H8O from 3 carbon graphites and 4 H2 gas and an oxygen. Okay. I think we said that that was a liquid. We didn't put those up there, did we? Oh, there should be a 2 right there. Gas. Oh, no, that's reacting with oxygen. What you doing, Miss Murphy? What you doing? No, it's not. Yeah, I noticed I left the CO2 right there. Okay. Did y'all see that? I just did. I don't want to have to redo all this. Any mistakes? I wish y'all could call me right now. Hold on, Miss Murphy, you left the 2 off right there. I wish. Man, that would be awesome. That would save me some time. Okay. We need to write our delta H for this. Right? It's given to us up here as -3. Oh, goodness gracious. -318 kilojoules per mole of the propan-2-ol formed. All right, so now what we have, guys, is starting where we were the last time. We have our target equation, and we need to manipulate these equations that we have written that are now at our disposal so that they will give us our target equation. And that's what we are going to start doing. We need to have 1 propan-2-ol molecule reacting. And right here, I have a propan-2-ol. I am going to flip this. So I will write C3H8O yields 3C graphite plus 4H2 gas plus 1/2 O2 gas. All right. And the delta H there is positive 318. I needed to change the sign. All right. Because I flipped it. Oxygen is present in 2 places. So I'm going to move past him and I'm going to look at my carbon dioxide. I've got 3 carbon dioxides produced. Right here, I have 1 carbon dioxide produced. So I will multiply that by 2 to give me 2. No, I will multiply that by 3. Hello. Go to bed. Okay. That gives us 3 graphites, 3 carbon graphites. I better get through this. Plus 3 O2 gas yields 3 CO2 gas. We multiply that by 3. So if I do the negative of 393 times 3 equals -1179. All right. And that's kilojoules per mole of that reaction, the way it's written. And then lastly, I've got 4 H2Os, make it a liquid. I don't care. They're the same. We've got H2. Okay, I need to multiply this by 4 because here I've got 1, but I need to have 4 of them. So I have 4 H2 gas plus 4 times 1/2 is 2 O2 gas yields 4 H2O. And does that need to be we'll make that a liquid, and the delta H of that is going to be the -286 times 4, up -286 times 4, -1144. Yeah. Alrighty, guys. Now let's make sure we've done the correct process and that our overall, in fact, matches our target, right? Remember, this is our target. Okay. This does not cancel. We do have 3 oops, sorry about that. We've got 3 graphites here and 3 graphites here, so those will be gone, right? We've got 4 hydrogens here and 4 hydrogens here, so those will be gone. Notice that we've got 3 plus 2 is 5 oxygens here. Over here we have a half of an oxygen. Something is wrong. Did I write something wrong? Times 4. 4 times 1/2 is 2. Oh, there you go. I did right here, didn't I? Is that 2? The graphite. This is 1/2. And y'all, let me tell you, I've literally been on this computer doing these for 4 or 5 hours now. I'm not going backwards. Graphite came from here. That was times 3. That is clearly a 3. Something is wrong with my oxygens. We'll get to it in a minute. I need to have 3. So this graphite here has a half, and that's there. This water here, which was multiplied by 4, has 1. That will be 2. That's here. Okay, let's just keep going. I've got 4 waters here. All right, I've got C3H8O liquid plus 4 O2. I'm so confused right now. Yeah, that's why. 0.502 yields 3 CO2 plus 4 H2O. That's right. That's right. This is 4.5. It all happened right there. OMG. I knew it was wrong. I knew it. I knew it. I knew it. I'm going to go take a nap. I'm so depressed.